Don't make fun of me. All right, we have a coin of mass M placed on a horizontal disc, and then the disc is rotating at a constant rate in the counterclockwise direction, and the static coefficient between the coin and the disc is mu. So first it just asked me to label and draw the vectors for the acceleration and the velocity. Well, for something moving in a circle, the acceleration, the centripetal acceleration, always points to the center. And at this point, going clockwise, the velocity would point straight up like this. And they're always perpendicular to one another. B is asking for the fastest speed that the disc can turn without the coin slipping off. So here we're talking about forces, so we're going to draw our free body diagram because this is not our free body diagram. That's acceleration and velocity. So if we look at it from this angle, the coin obviously feels a weight force or a force of gravity down, and then the disc is holding it up. That would be my normal force. And the force that is directed towards the center, that is keeping the coin moving in a circle, is the friction force. Because if there wasn't friction, as soon as the disc starts turning, then the coin would slip off. So this is the friction force directed to the center, which means my friction force is the centripetal force. Now, there's only so much static friction that the coin and the disc can't hold, right? Because it has some...
Cesar Gonzalez, please report to the main office. Cesar Gonzalez, please report to the main office.
So there's only so much static friction, so there's going to get to a point where it goes too fast and the static friction is not enough to hold it in place. So that's the point where the most static friction, the mu Fn, is equal to that centripetal force. So mu Fn, or sorry, force of friction is mu Fn. Centripetal force is mv squared over r. And in this case, my normal force is just equal to the force of gravity, which is mg, and this is mg. So I've got mu mg equals mv squared over r. If I have a mass on both sides, those cancel out. I'm looking for velocity, the speed, so I'll multiply r up. So I've got mu gr equals v squared. Last step is to square root, and you get that the velocity is the square root of mu gr. And I checked, there's nothing I'm not allowed to have. I'm allowed to have mu and g, the constant, and r in there. Now, C is asking if I were to repeat this, but with a second identical coin glued to the top of the first coin, how would this affect it? Well, if you're adding a coin, then you're adding more mass. So that would be more mass. And if we look at our equation, the velocity depends on the radius and the coefficient of friction. So there is no dependence on mass, so there would be no effect. No effect because the velocity does not depend on the mass. And your reasoning is like that equation you just came up with. Now, number 2, we've got a space shuttle that is moving in a circular orbit at some altitude above the Earth's surface. The space shuttle is then rising to a higher orbit, so think of higher orbit as a bigger radius. And the speed in this newer orbit, well, let's think about how does speed relate to the velocity. So we're talking about the centripetal force, and the centripetal force here is the gravitational force. Centripetal force is mv squared over r. Force of gravity is big G m1 m2 over r squared. One of the masses cancels out, one of the radiuses cancels out. Square root, your velocity is the square root of gm over r. So what I am doing is I am changing the r to a bigger r. So if this is getting bigger, when you divide by a greater radius, that means you have a slower velocity. So then your velocity would be less than in the lower orbit, because as you get farther away, you have less speed. Oops, checked off less. Now the period. So let's think about period is the time for one revolution around the Earth. So we know that the velocity is equal to this. The velocity is also how far it goes in that one loop around. So that's just the circumference of the circle, 2 pi r, and the time that it takes. So if we multiply up, that would be tv's 2 pi r, divide the velocity over. So the period is just 2 pi r over velocity. So here I am increasing this, because that's the whole point, is I go to a bigger radius. And we've already decided that v would be slower, so this is decreasing. If you multiply by a bigger number, it gets bigger. If you divide by a smaller number, it also gets bigger. So this is going to be greater than the orbit. And you can use this like algebraic reasoning, or you can say it has farther to travel and is slower, so it takes more time. That would also be a great explanation. And then the acceleration in this higher orbit, so your centripetal acceleration is v squared over r, and we said that this is slower and that your radius is bigger. So if you have a direct dependence of the velocity, so slower velocity is a greater, or not greater, is less acceleration, and greater radius is less acceleration. So this should be less in the lower orbit. You also can use, so the centripetal acceleration is also the acceleration due to gravity, the little g, which is gm over r squared. So you also can use this dependence. So a greater radius, you're dividing by a greater number, so that makes the acceleration due to gravity smaller, so smaller acceleration. Because your acceleration due to gravity is your centripetal acceleration here. We've got a ball of mass m attached to a string of length r, twirling around in a vertical circle, so this is like up and down. When the ball is at point P, the string is horizontal, point Q is at the bottom, Z at the top, and we're going to express all of our answers in the givens that it tells us. So it says draw out all the forces at points P and Q. So if we look at point Q, well, at every point it feels a weight, and then at this point the tension would be in towards the center because that's the way the string would be pulling it. So just the force of gravity down and tension to the center. At point Q, still feels the force of gravity down, and my tension would be up towards the center, and your tension would have to be greater than your force of gravity because it is accelerating up, because the centripetal force is up to the center of the circle. At which point would this tension be the greatest? So we've drawn here and here. If you were to draw for Z, your gravity and your tension would go in the same direction. So the point where your tension would be the greatest would have to be Q, because your tension is overcoming or going against the force of gravity, so it must be greater there to keep the same centripetal force. And the reason you have the same centripetal force is because it said it's at a constant speed and the same radius. Now it doesn't tell me it's keeping the same radius, but if you have an object moving, twirling around in a circle, you can assume that the string is staying the same length. At point Q, the tension is 4 times the weight of the ball. Solve for the velocity of the ball. So let's look. Here, my centripetal force at point Q would be the tension minus the force of gravity because they're going in opposite directions. Force of gravity is just mg, and tension at this point is 4 times the weight of the ball, so that's 4 mg. And that would equal my centripetal force, which is mv squared over r. So that means mv squared over r is equal to 4 mg minus mg is 3 mg. Masses cancel out, and we're looking for velocity. Multiply the r up, and then take the square root. So velocity is the square root of 3 mg. If the ball was twirled at the same speed but at a larger radius, would the tension be more or less than calculated? So we can't just look at this dependence because this velocity was the velocity we solved for if we already knew the tension. So we can't just look and say, oh, it doesn't depend on mass. Oh, sorry, Bistro. So what we're going to look at is like your free body diagram. So think about if the radius is larger and hold on, keeping the exact same speed. So if you keep the same speed, FC mv squared over r, if I keep the same speed but this is larger, then that means that this is less. And then your tension, we had just said, was FC plus mg. Well, if this is less and the weight hasn't changed, then this would have to be less. So here, because we have a less centripetal force, then we would have less tension in the string. And the reason we have less centripetal force is because we have the same speed but at a greater radius. And D, suppose the string breaks at the instant the ball is at point P. So if we look at point P, this was going around counterclockwise, so this was directly, the velocity was directly up. And we want to know, just describe the motion immediately after the string breaks. So it's going to obviously go up because it has some initial velocity and then fall back down because it is vertically. So gravity is going to pull it back down. So it'll be, I'll say the ball goes flying up with an initial velocity of square root of 3 mg, which is what we just calculated. So we calculate the velocity at point P. No, that would be the velocity at point Q, but it's constant velocity, constant speed. So that's also my speed at point Q. So it'll go up with some initial velocity of square root of 3 mg up and will fall back down because gravity accelerates it down. Pardon my terrible handwriting on this. Part 2 is asking how high it would reach after the string break. So let's think about, if I want to know to the very, very top it goes, well, I know my initial velocity is square root of 3 mg. I know the final velocity, or the velocity it's going to go to at the top is, going to be 0 because it has to stop at the top to fall back down. And we also know the acceleration is just little g. Now I'm going to put a negative sign because we haven't been using like the direction down for our little g up here. We kind of took care of it because we subtracted the fg, but I need to make sure my acceleration is in the opposite direction to that initial velocity. And we're looking for how far it's going to go, so that's like our delta x. So we can use our v squared is v naught squared plus 2a delta x equation. V is 0. V naught is square root of 3 mg. That gets squared plus 2g delta x, and that g is negative, so I'm going to make that a minus sign. When you square a square root, that cancels out, so 3 mg minus 2g delta x. Move this over, you get minus 3 mg equals minus 2g delta x, divide by the negative 2g. G's cancel, negatives cancel out, and that means 3/2 the mass is your delta x. Oh my god, I'm so annoyed at myself. I crossed these m's off, and that's r, not m right here. I'm so sorry, guys. That was an r right here because the m's cancel out and you're left with an r. And then that means this is an r. Just replace all these m's with an r because I am doing this really fast and I called it m, not r. Because it doesn't make sense that your distance is 3/2 of a mass. It makes sense that your distance is 3/2 of the radius. So hopefully you see what I did. I had already crossed off the m's and I'd multiplied the r up, and I just write m instead of r right here. So it's actually an r right here. And the time it would take, well, you can use your v equals v naught plus at equation. You already know v naught is the square root of 3gr minus gt equals 0. Move this over, so gt is the square root of 3gr, and then divide by g. Now you cannot completely cross off the g's because this one is the square root and this one is not. So you can leave it as the square root of 3gr over g, or you can say square root of g over g. That is just the square root on the bottom, so it's the square root of 3r over g. But if you just leave it like this, then you're totally fine. My bad about the m becoming an r, or r becoming an m earlier.